I'm a senior director in pharmaceutical development at Pharmaceuticals, and thank you again. It's really nice to meet everyone virtually. And very good morning, good afternoon, good evening, depending on wherever you're in the world. Where I am, it's like 6 in the morning in the East Coast of the United in the East Coast of the United States.
A nice way to start your day.
Yes, indeed. Should I share my screen, or is someone going to share my slides?
You can share your screen.
Okay, sounds good. Let me do that.
So Dr. Arul from Avanir Pharmaceuticals, right?
It's actually Otsuka. I think there was a mistake that they used my old company name instead of my current company name.
Okay.
It's actually Otsuka. Otsuka Pharmaceuticals is my employer. Avanir is actually a subsidiary of Otsuka. I used to work at Avanir, and then we were fully integrated into Otsuka. And so you could see, hopefully you can see my slide here.
I can see your slide, and the stage is yours. The virtual stage is yours, please.
Perfect. Thank you so much, Paula. So my talk today is going to be on techniques to improve bioavailability of drug products, and mainly, focusing on solid dispersions. And one particular solid dispersion technique, which I feel that hasn't been, used as much, especially in the industry, which is spray congealing. And there are some advantages of using spray congealing compared to the other techniques that we have. And again, you have my name and my affiliation. I've worked with Otsuka Pharmaceutical Development and Commercialization. And to start out with just a disclaimer that, whatever I express here is just my opinion. It has nothing to do with my employer or the conference organizer or anyone else affiliated with me or my company, right? This is just a legal requirement that we have this when we give presentations. So that's why I have this slide. And here's the agenda, right? So basically, I would start out with just introducing solid dispersions for the for the members of the audience here who want to be reminded of what they are. Some of the solid dispersion preparation technologies, and some of these are very well known, like spray drying, which is very well used, and I've used it in my past as well. Then, to introduce spray congealing process, equipment, excipients, and characterization. And finally, we'll look at some of the mechanisms. And with that, we'll end with the question and answers. And if anyone has any questions, please don't hesitate to interrupt me and ask a question, right? Happy to answer any questions you have. So solid dispersions, right, are, as we all know, are inert systems in which the drug is dispersed in a solid inert matrix, right? And typically it is, you have a hydrophobic drug and you use a hydrophilic matrix. And this is typically a polymer that you use. And the way in which solid dispersions improve oral bioavailability is to allow a rapid release of the drug in a supersaturated state above its equilibrium solubility. So typically this is used for BCS2, BCS4, where you have very low solubility in the crystalline state. And so you try to take the drug into a higher, equilibrium solubility state, and stabilize it using a matrix, a hydrophilic matrix, and then you release it. When it's released orally, it immediately comes out at a higher equilibrium state, like an amorphous state, which has a higher energy, and you have greater solubility, and thereby greater bioavailability. Now, looking at the typical ways in which we make solid dispersions, we have three methods, right? We have solvent-based methods, mechanochemical methods, and melt-based method. Solvent-based method is the most commonly used technique, which is spray dry dispersion to make amorphous material of the drug. And this is the most widely practiced technique. And of course, then we have high energy milling, which is also widely used to make amorphous drug stabilized with a polymer and then released. And finally, we have the melt-based methods. And hot melt extrusion, again, is a widely used method for making solid dispersions and to improve bioavailability. So let's take a quick look at each one of these before we move to spray congealing. Spray drying is a versatile, widely used technique to improve solid dispersions. Some of the disadvantages we have with spray drying is it has a relatively high process temperature. You have to use solvents, and the particle size distribution can be small. And some of these, for most needs that you have for a drug molecule, this might fit. But when your drug molecule is sensitive to high temperature, it's sensitive to the use of solvents, then solid spray dry dispersion may not be the ideal option. So then you might want to try using other techniques, such as some of the other techniques that we talk about. And I would like you to consider spray congealing at the very end as a very good option to try as well. So we talked about the second technique being mechanochemical activation. So this is all types of high energy milling that is considered, right? So anytime we use jet milling or other milling techniques to create this high energy state, amorphous state, here the issue that happens is with using mechanical energy, you're actually disrupting the crystal lattice, right, of the APIs that you use. And this can lead to polymorphic transformations, crystal defect generation, amorphization, and other additional physical and chemical changes in a crystalline drug. So sometimes the issue with milling can be that if you have a particular polymorph, you want to keep it that polymorph. When you use high energy milling, there is the possibility that you could have polymorphic transformations that happen, and that can lead to lower solubility and lower bioavailability, right? And finally, the melt-based methods, and hot melt extrusion is the most widely known melt-based method, right? The key advantages of using hot melt extrusion are lack of solvent, right? So if your API is sensitive to solvent, it's good that you can use HME because HME doesn't have solvent. So you don't have the issues with toxicity related to the presence of organic solvents, because when you have organic solvents, you need to worry about the ICH, International Council of Harmonization, limits for what the drug can contain, how much it can contain. So, you don't have the issues associated with having organic solvents, which you do with spray dried dispersion. And you also have the advantage of using hygroscopic and water sensitive drugs, which are always an issue with other techniques, right? The other two techniques that we saw. So this is a widely used technique. What are the one limitation of HME is HME is going to, you would need a downstream process to obtain the desired particulates that you need, right? So you're not going to get, so at the end of the HME process, what you get are noodles, right? You don't get the particulates that you need for encapsulation or for tableting. So typically what we do is we have a spheronization that we do as a process downstream of HME to get the to get the product in the form that we need, right? Which is multi-particulate systems. Finally, we are looking at spray congealing. And this is what I wanted to introduce during this presentation today, was a technique that is, it's not as widely practiced, but I think it's a very useful addition to the arsenal that we have for creating, for making solid dispersions. So the advantages of spray congealing are, it is a very simple and scalable process. It is solvent free. It is less time and energy consuming compared to some of the other techniques that we looked at. It has free-flowing microparticles suitable for tableting or capsule filling without need for downstream processes such as drying, milling, or granulation that you have with other techniques, right? And the one other big advantage with spray congealing is it has high encapsulation efficiency. It has about 90 to 100% encapsulation efficiency, which is a big advantage. And also, I have to stress the fact that the microparticles that you get from spray congealing are very spherical and free-flowing. So it's a big advantage. So it's a good complement to the existing technologies that we have. So taking a look at the process itself, the process is fairly similar to spray drying. The difference is that we don't use a solvent to dissolve the compound. So what we do is we take the carrier, right? So the excipient is melted typically, and it's the excipient that we typically use for spray congealing are low melting polymers. So you warm the polymer, melt it, get it above its melting point, then you dissolve the API in this molten fluid. So this results in the formation of a single phase liquid mixture because the API is solubilized in the molten carrier, the polymer that we use. The second step is atomization, right? So you nebulize the molten fluid stream that you have by using an atomizer. And this small droplets that you form are immediately cooled at room temperature, and they solidify in the cooling chamber to form solid spherical microparticles. So it's a very, very simple technique to use. And some of the equipment that we use are, you need to have a pump, right, to transport the feed to the atomization device. And typically we use peristaltic pumps to do this. And one of the things that we need to be careful about is the feed viscosity. If you have too viscous a feed, you might clog the tubes and you may not be able to produce a good, may not be able to get a good transportation of your molten liquid from the chamber to the atomization device. And then we have different forms of atomizers, and atomizers are similar to what we use for spray drying. And these can convert the molten fluid into small droplets by, applying pressure and, pushing the liquid through a narrow nozzle at high velocity. And the typical type of nozzles and atomizers that we use are the rotary nozzle atomizers, hydraulic or pressure nozzles, pneumatic nozzles, and ultrasonic nozzles. Now we'll take a look at more at the carrier, the excipient that is used. And as I mentioned, it should be low melting. And typically, what is chosen is any excipient that can melt between 35 to 90 degrees. And the most commonly used are PEG, gelisaires, and poloxamers. Polyethylene glycol PEG is most widely used because of its low toxicity and cost. The low, the low TG values, for PEG crystallization, right? The glass transition temperature for PEG is fairly low. And, so it allows the API to be dispersed in the semi-crystalline and, multiple microstructures can be formed with PEGs itself. The solid PEGs typically have a molecular weight of 1,500 to 6,000 gram per mole. And the second polymer that is widely used are gelisaires. And gelisaires are mono, di, and triglyceride esters of PEG. And they're typically semi-solid, waxy, amphiphilic material. And they're typically used due to their ability to form dispersed systems in water. So they have the advantage that they form these dispersed systems in water. And the typical gelisaire that is used is a gelisaire 5013. Finally, we can use poloxamers. Poloxamers are again ABA type tribroc copolymers based out of polyoxyethylene and polyoxypropylene with a high solubilizing capacity. They are amphiphilic. They're very useful non-ionic surfactants. They have low toxicity and compatibility. One of the limitations of using poloxamers is their high viscosity in the molten state. So when we are choosing these, we have to, as I mentioned previously, we need to make sure that the viscosity is not too high, because then we'll have problems transporting the solid dispersed molten liquid from the reactor to the atomizer. And one of the poloxamers that's commonly used is Poloxa 407. And So these are some of the techniques that are used to characterize the spray congealed solid dispersion that is formed. So typically for drug content, you use chromatographic and spectroscopic techniques like HPLC, UPLC. For solid state properties, we typically use DSC, XRPD, solid state NMR, right? PLM, HSM. Morphology, for morphology, we use SEM, OM, size, like laser light sieves for determining the size, or laser light scattering. And also for morphology, you can do the surface area. For manufacturability, we do the density, flowability, contact angle. For drug carrier interactions, DSC again, HSM, FTIR, SS solid state NMR, right? And for in vitro testing, obviously, we use solubility studies, in vitro drug release, dissolution studies, and permeability studies. So these are the typical characterization techniques that are used for spray congealed solid dispersions. So now, what is the mechanism of bioavailability enhancement of spray congealed systems? So some of these are the possible mechanisms that are proposed, when you have created this API solid state, which is like an amorphous state, a high energy state, which is a supersaturated state. What we expect is it improves wetting. Now, it increases the contact between API and water because you are already dispersing the API, right, in the matrix. It enhances solubilization by reducing aggregation and agglomeration, which is an issue that you have with APIs. It allows for the formation of dispersed systems. So you have these self-emulsifying colloidal systems like Gelucer, right? Which allows the Gelucer allows it to form these dispersed systems when you mix it with water. And obviously, you have the reduction of drug particle size, right? And that is typically when you use that ultrasound, you do have that. And as I mentioned, with spray congealing, typically you form these atomized small microparticles, which are very uniformly distributed. So some of the mechanisms, again, is where the API solid state is modified. So the previous example we looked at where the API solid state is the same, it is not changed, right? So for instance, if you have a crystalline API, you still keep it crystalline, a semicrystalline API, semicrystalline. So here it is modified. So the API solid state is modified by spray congealing. So here, what happens is the API interacts with the molten carrier are strong. So for instance, you make an amorphous, or a semi-amorphous form. During the cooling phase, right, the solubilized drug solidifies in disordered cluster. So it is maintained in its amorphous form within the carrier matrix. And this amorphous solid having a higher solubility, when you take it orally, it allows for it to have a higher solubility in vivo. Secondly, during step 3 cooling phase, the solubilized drug may also crystallize into different polymorph. And this polymorph might be a metastable form, and that allows for it to have a higher energy compared to the most thermodynamically stable form, which has lower solubility. So these are a couple of the mechanisms by which, when you are modifying the solid state of the API using spray congealing, that you're improving the